Good morning, students. So in the 10th unit, next we are going to the last two topic of this lesson, that is oscillation of a simple pendulum in a simple harmonic motion and loss of simple pendulum and energy in a simple pendulum. So first of all, we are going to see the simple pendulum. So you know the pendulum clock. So a pendulum, it's a mechanical system and which will be exhibits with a periodic motion. So it will have a bob that will have a mass and that will be suspended with the long string. Okay, and the other end is fixed on a sand. So at equilibrium, the pendulum does not oscillate and hangs vertically down. So such a position is known as a mean position or a equilibrium position. So if the pendulum is displaced through a small displacement from its equilibrium position and again released, the bob of the pendulum executes to and fro motion. Let L be the length of the pendulum, which is taken as a distance between the point of suspension and the center of gravity of the bob. So the two forces act on the bob of the pendulum at any displaced position. That will be one as a gravitational force that is acting on the body, which acts vertically downward. That is, we know that what is a gravitational force, F is equal to mg. And the next one is a tension of the spring. So that will act as along the string to the point of suspension, that will be taken as T. So for resolving the gravitational force, that will be having two components, that is one is a normal component that will be along the string but opposite in the direction of the tension, that is Fs As is equal to mg cos theta. And another force is tangential component, so that is a component perpendicular to the string that along the tangential direction of the arc. So that is Fps is equal to mg sin theta. So this is a perpendicular string, this is a long string, that's why they are mentioned as a long string as a As and perpendicular string as a Ps. So now the normal component of the force is along the string, that is T minus Fas, that is equal to, so we are substituting the value, and that will be, we are getting as m into v square by L. Okay, and that the v is the speed of the bob. So T minus mg cos theta will have the value. Why we are substituting the mg cos theta? Fas is nothing but mg cos theta. So T minus mg cos theta is equal to m into v square by L. Okay, and then we observe that the tangential component Wps of the gravitational force always point towards the equilibrium position, that is a direction which always opposite to the direction of the displacement of the bob from the main position. So that's why the tangential force is nothing but a restoring force. By applying the Newton's second law along the tangential direction, we have the m d square s by dt square plus fps is equal to 0. That is fps minus fps is equal to m d square s by dt square. So s is the position of the bob which is measured along the arc. So expressing arc length in terms of the angular displacement, that is s is equal to L theta. Then what is its acceleration? D square s by dt square is equal to L into d square theta by dt square. Excuse me. So we are substituting this in this equation. So we'll get that L d square theta by dt square is equal to minus g m, that is minus g sin theta. So what is the d square theta by dt square? That is g minus g by L sin theta. Because of the presence of a sin theta in the above differential equation, it is a non-linear differential equation. So it's a homogeneous second order. So the small oscillation approximation, sin theta is approximately equal to theta. So then the above a differential equation becomes a linear differential equation, that is d square theta by dt square is equal to g minus g by L theta. This is well known, that oscillatory differential equation. So the angular frequency of this accelerator is equal to omega square g by L. So omega is nothing but g by root of g by L, that is radian per second. Frequency is f is equal to 1 by 2 pi root of g by L hertz. So time period, it's reciprocal, that is t is equal to 2 pi root of L by g. So these are all the simple harmonic motions. Okay, and Next we pass on to the law of pendulum. So the pendulum depends on the following laws. That is a law of length. For a given value of acceleration, it is due to gravity. So the time period of a simple pendulum is directly proportional to the square root of the length of pendulum. That is t is proportional to root L. Next, a law of acceleration. For a fixed wavelength, the time period of a simple pendulum is inversely proportional to the square root of the acceleration due to gravity. That is, t is proportional to 1 by root g. So, independent of the following two factors, one is the mass of the bob. So, the time period of oscillation is independent of the mass of the simple pendulum. This is similar to free fall. So, in a pendulum, the fixed length does not matter whether an elephant swings or an ant swings. Both of them will swing the same time period. Okay, so both will be having the same. And next, the amplitude of the oscillations. For a pendulum with the small angle approximation, angular displacement is very small. So time period is independent of the amplitude of the oscillations. Okay, understood what are the things as to be given. And for that, these laws are the laws of simple pendulum, very important one. And next we pass on to the energy in the simple harmonic motion. So for expression for the potential energy, in the energy means it's a potential energy and then kinetic energy and the total energy. Okay, so for the expression for the potential energy, for a simple harmonic motion, the force and the displacement are related. You know what is Hooke's law. And for the force, that is minus k into r. So force is a vector quantity. In a 3-dimension, it has a 3 components. So the force in the above equation is a conservative force field. So such a force is derived from a scalar function which has only one component. So in one-dimensional case, F is equal to minus kx. So we have discussed in the unit of 4, that is volume 1, work done by a conservative force field is independent of the path. So the potential energy U can be calculated from the following expression, that is F is equal to minus du by dx. So what is minus du by dx? That is equal to minus kx. So du is equal to kx dx. So work done by the force F during the small displacement dx stored as a potential energy. So u of x, we are giving the integration, that is 0 to x, k x dash dx dash, that is of k x dash, that is square. You know how to integrate, and then limit substitution. So you are getting of kx square. So we can substitute the value of force constant k, that is m omega square. So you will get u of x is equal to of m omega square x square. So omega is a natural frequency of the oscillating system. So for simple harmonic motion, the particle executing, that is we get x is equal to a sin omega t. So if you are substituting in the u of t, that is we will get of m omega square a square sin square omega t. So this is a variation of the u, that is for the different time periods. Okay. So next we are pass on to the kinetic energy expression. Kinetic energy, we know that is of mv square. We are taking here as a mvx square. So for that, vx is nothing but the velocity. So that is displacement by time taken. For that, we are substituting that as dx by dt. So the simple harmonic motion, the particle executing in this kinetic energy. So x is same, x is equal to a sin omega t. So velocity we are going to write as, so derivating the x, we are getting a omega cos omega t, and then is equal to a omega, then the root of 1 minus x by a whole square. So that is Vx is equal to omega root of a square minus x square. So kinetic energy, in this we are substituting that, you will get of m omega square a square minus x square. So k is equal to of m omega square a square cos omega square t. So this is also the graph we are getting for the kinetic energy for the different time periods. Next we are going to write the expression for both the energies. So the sum of both the energies, so that is the potential energy plus kinetic energy. So we will get of m omega square a square minus x square plus of m omega square x square. So both the terms plus and negative terms will get cancelling, and you will get of m omega square a square, that should be a constant one. So for the alternatively from the equation, the two equations, will get the total energy, that is of m omega square a square sin square omega t plus of m omega square a square cos square omega t We know the value of sine square omega t plus cos square omega t, that's equal to 1. So you will get the equation from the trigonometry identity. So we'll get that final equation as E is equal to half m omega square a square, that is also a constant. So this gives a law of conservation of the total energy. This will be a graph for the both the kinetic energy and potential energy varies, but the total energy is a constant one. So the amplitude of the simple harmonic oscillator can be expressed in terms of A is equal to root of 2e by m omega square. That is equal to root of 2e by k. Okay, so this is the expression for the final equation. Understood? So up to this your unit has to be over, the 10th unit. And next the video class we will getting for the 8th unit.